Right now, as you sit perfectly still, roughly 99% of what you call your weight is not made of solid substance at all. It is trapped energy, restless fields held in place. And it is that energy, not any lump of matter, that bends the space around you. This is the quiet scandal hiding inside general relativity, Albert Einstein's 1915 theory of gravity, and inside the mathematical object at its core, the stress-energy tensor, written T mu nu, the 16-component ledger of energy, momentum, pressure, and stress that Einstein's field equations name as the true source of gravitation, not mass. Mass is only one small entry in that ledger, and in ordinary matter, a startlingly small one. Stay with me, and you will understand why the single word we lean on most when we talk about gravity, mass, is, at the deepest level, a bookkeeping label rather than a cause. You will see why a spinning planet drags space in a spiral, why pressure inside a dying star can hasten its own collapse, why a passing gravitational wave leaves a permanent scar on empty space, and why the proton in every atom of your body weighs almost nothing on its own, its heft borrowed entirely from the energy of the forces raging inside it. If you find value in explorations like this, the subscribe button quietly helps these deep dives reach more curious minds. No fireworks, just one more person here for the next impossible question. We will move from Einstein's equations to neutron stars, to precision satellites, out to the frontier, where gravity itself may not be fundamental at all. And we will resolve what the evidence actually shows. So here is where it begins. For 3 centuries, the story of gravity was a story about mass. Isaac Newton gave us the law that shaped the modern world. Every particle of matter attracts every other with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Mass was the source, mass was the currency. Put more mass in a place, and gravity grew stronger there. The law was clean, it was predictive, it launched spacecraft and charted planets. And for most everyday purposes, it still works beautifully. When engineers plotted the trajectory that carried Apollo 11 to the Moon in 1969, Newton's mass-based law was more than adequate. But Newton himself was uneasy. He described how gravity behaved with breathtaking accuracy. Yet he confessed he could not say what it was, or how one body could reach across empty space and pull on another. That honest gap sat unresolved for over 200 years. When it finally closed in November of 1915, the answer did something no one expected. It did not refine the idea that mass is the source of gravity. It replaced it. Einstein's general relativity does not describe gravity as a force pulling masses together. It describes gravity as the curvature of space-time, the 4-dimensional fabric of 3 space dimensions and 1 time dimension, bent and shaped so that objects moving freely through it follow curved paths that we experience as falling. A dropped apple is not being pulled. It coasts in a straight line through a geometry that has been curved. And the question that matters for everything that follows is deceptively simple. What curves it? Here the old story breaks. The source of that curvature, in Einstein's equations, is not mass. It is the stress-energy tensor, T mu nu. And the difference between those two ideas is the entire subject of this exploration. Let me state the equation, because it is the spine of everything, and because this audience deserves to see it rather than be told about it. The Einstein field equations read G mu nu plus lambda G mu nu equals 8 pi G over c to the fourth times T mu nu. Let me unpack every piece in plain language. On the left, G mu nu is the Einstein curvature tensor, a precise description of how space-time is bent at a given point. The term lambda G mu nu carries the cosmological constant, lambda, multiplied by the metric G mu nu, which is the object that defines distances and durations in space-time. We will return to lambda much later, because it hides one of the deepest open questions in physics. On the right, 8 pi G over c to the fourth is a conversion factor built from Newton's gravitational constant G and the speed of light, c. It sets the exchange rate between energy and curvature. And then there is T mu nu, the stress-energy tensor, the source. That is the whole architecture. Curvature on the left, T mu nu on the right, and an equals sign that says, tell me the energy and momentum content of a region, and I will tell you exactly how space-time bends there. The physicist John Archibald Wheeler summarized it in a line that has become famous. Space-time tells matter how to move, and matter tells space-time how to curve. But notice what matter smuggles in. The thing on the right side of the equation is not matter in the sense of stuff you can hold. It is T mu nu, a tensor. So what is a tensor? And why does it matter that gravity's source is 1? Think about a weather report. If I tell you only the temperature outside, I have given you a single number, what physicists call a scalar. Mass, in the way we usually mean it, is exactly this: one number, no direction, no structure. But a real description of the atmosphere needs more. It needs wind speed and direction, which is a vector, a number with an arrow. And if you want to describe the shearing stresses inside a moving fluid, or the pressure pushing outward in every direction at once, you need something richer still, a tensor, an object that carries a whole grid of related quantities. The stress-energy tensor is a 4x4 grid, 16 entries, of which 10 are independent because of its symmetry. Each entry means something physical. Picture the grid laid out. The single entry in the top left corner, written T00, is the energy density, how much energy sits packed into a given volume. The top row and left column, the T0I components, encode energy flux and momentum density, energy flowing, matter moving. And the inner 3x3 block, the spatial part, encodes the pressures and the shear stresses. The diagonal entries are pressure pushing outward, and the off-diagonal entries are shear, the sideways dragging forces within a material. Now, hold that image, because here is the claim that reorganizes everything. every single one of those entries gravitates. Not just the energy density in the corner, the pressure gravitates, the momentum gravitates, the shear stress gravitates. Rest mass, the thing Newton called the source, does not even appear in the tensor as its own separate entry. It shows up only indirectly, folded into the energy density, and even there, it is usually a minority shareholder. Think about a surveyor hired to map a property. If she measured only the length of the north fence and reported that as the property, she would miss the width, the elevation, the shape of the boundary, everything that makes the land what it is. Newton, in effect, measured one fence. Einstein handed us the full survey. And the full survey says what you called the source was one line item in a much larger account. Before I continue, consider what this means. Take a moment. If pressure gravitates, then squeezing something changes how it curves space-time, independent of adding any matter to it. If momentum gravitates, then a moving object curves space-time differently than a still one, not because it gained mass, but because motion itself is a source. We will test both of these claims against real experiments before we are done. For now, plant a flag here. Gravity's source is a tensor, and rest mass is only one small, frame-dependent slice of it. We will return to this. Let me make the second equation concrete, because it shows exactly where pressure enters the story. For a simple idealized substance, what physicists call a perfect fluid, a good model for the inside of a star, the stress-energy tensor takes the form T mu nu equals rho plus P over C squared times U mu U nu plus P G mu nu. Here, rho is the energy density, P is the pressure, U mu is the velocity, describing the fluid's motion through space-time, and G mu nu is the metric. Read it slowly, and you see the crucial feature. The pressure P appears twice, woven directly into the source. It is not a passive bystander. In Einstein's gravity, pressure is an active ingredient of gravitation. To Newton, this would have been nonsense. Pressure is what holds things up, the outward push of gas that keeps a balloon inflated, the resistance that lets a bridge bear a load. The idea that the very thing resisting collapse could also feed the gravity that causes collapse runs deeply against intuition. And yet, it is written plainly in the equation, and nature, as we will see in the hearts of dying stars, obeys it. What does it mean that the outward push holding a star up is, at the same time, part of what pulls it down? Hold that question. We will return to it in the story of neutron stars, which is where this abstract feature of the equations becomes a matter of life and death for a star. Let me now address the word mass directly, because we cannot go further without being precise about what it even is. In special relativity, Einstein's 1905 theory of space and time at high speeds, we describe a particle by its 4 momentum, written p mu, a 4 vector whose time component is the energy divided by the speed of light, and whose space components are the ordinary momentum. From that 4 vector, you can construct a quantity that every observer, no matter how fast they are moving, agrees on. That quantity is the invariant mass, and it obeys the relation E squared equals pc squared plus mc squared, all squared. In words, energy squared equals momentum times c squared plus rest mass times c squared squared. Let me unpack it. E is the total energy. P is the momentum. M is the invariant or rest mass. The reason this equation reveals so much is what happens to M. It is what mathematicians call a Lorentz scalar, a number that stays the same for every observer in every frame of reference. Your speed, relative to a particle, changes its energy and changes its momentum, but the combination that gives m stays fixed. Mass, in this precise sense, is not a substance. It is an invariant label, a fingerprint you compute from the four momentum. Think about a locksmith reading the cut pattern of a key. The pattern is a fixed property of the key. Turn the key over, shine different light on it, carry it to another city, and the pattern does not change. But the pattern is not what opens the door. The physical engagement of the pins is. Rest mass is like that cut pattern, a genuine invariant property useful for identification, but not itself the mechanism that does the work. The mechanism that curves space-time is the full stress-energy tensor, and rest mass is one invariant you can read off from part of it. This is the part that stays with me. Not that mass is unimportant, it is a real and precise quantity, but that we spent 300 years mistaking a label for a cause. When I first understood this, I had to sit with it for a while, because it quietly rearranges what the reason things fall even means. Now, if rest mass is only one small entry, and gravity's real source is energy and momentum and pressure, then a natural question follows, and it is the question that turns this from abstraction into something visceral. How much of ordinary matter's gravitating mass is actually rest mass, and how much is energy in disguise? To answer that, we have to go inside the atom, down into the proton, and the answer is genuinely astonishing. Consider the proton, one of the two building blocks of every atomic nucleus, and therefore of every atom in your body, in the chair beneath you, in the earth under that. The proton has a mass of 938.27 million electron volts in the units physicists use, which works out to about 1.673 times 10 to the minus 27 kilograms. That mass is what makes matter heavy. That mass is what sources the gravity of the entire planet. So where does it come from? The proton is made of quarks, 3 so-called valence quarks, 2 up quarks and 1 down quark, bound together by the strong nuclear force, which is carried by particles called gluons. Here is the number that should stop you. The up quark has a rest mass of about 2.16 million electron volts. The down quark about 4.67 million electron volts. Add up the rest masses of the 3 quarks that supposedly make up the proton, and you get something on the order of 9 million electron volts. But the proton weighs 938. The rest masses of its constituent quarks account for only about 1% of its total mass. A lattice QCD determination, published in the journal Science in 2010, found the up quark weighs about 2.01 million electron volts and pegged it at just 0.214% of the proton's mass, a factor of roughly 435 times smaller than the whole. So where is the other 99%? It is energy. It is the ferocious energy of the gluon fields binding the quarks, the kinetic energy of the quarks racing around inside at near light speed, and a subtle quantum effect called the trace anomaly. In 2018, a team led by the physicist Yang and collaborators published in Physical Review Letters a full decomposition of the proton's mass using lattice quantum chromodynamics, the computational method that simulates the strong force on a grid of spacetime points. Their result, in round numbers, the quark kinetic energy contributes about 33%, the gluon field energy about 37%, the trace anomaly about 23%, and the quark scalar condensate, the only piece genuinely tied to the Higgs mechanism, the only piece that is rest mass in the sense people usually mean, only about 9%. And of that, only 1 to 2% of the proton's mass is truly the intrinsic rest mass of the quarks. Let that land. The overwhelming majority of the mass that makes you heavy, that sources your gravity, that presses you into your seat, is not stuff at all. It is confined, restless energy. Picture two accountants auditing a company that everyone assumes is rich in physical inventory, warehouses full of goods. They open the books and find that 99% of the company's stated value is not inventory at all, but the frantic, ceaseless motion of money circulating internally. The company is real, its value is real, but its worth is almost entirely activity, not substance. The proton is that company. What does it mean that nearly all of your weight is trapped energy rather than matter? It means Einstein's equation was telling the truth all along. Gravity's source is T mu nu, energy and momentum and pressure. And when we finally learned to look inside the proton, we found that even the thing we call mass is, at its core, energy. There is a beautiful equation lurking here, the QCD trace anomaly, which reads theta mu mu equals beta of g over 2g times the trace of g mu nu plus the sum over quark flavors of mi psi bar I psi I. The first term, the one built from the gluon field strength g mu nu and the QCD beta function, which describes how the strong force changes with distance, is where most of the proton's mass comes from. The second term, the one with the quark masses mi, is the small Higgs contribution. The mathematics says plainly, hadron mass is overwhelmingly gluonic energy. I want to sit with something a scientist named Wheeler saw long before we could measure any of this. Back in 1955, in a paper in Physical Review titled simply Geons, John Archibald Wheeler asked a question that sounds almost like a riddle. Could you make an object that has mass, that gravitates, that would deflect a passing particle just like a planet, but that contains no matter at all? no rest mass anywhere inside it, only field energy held together by its own gravity. He called such an object a geon, a contraction of gravitational electromagnetic entity. His idea was to take a bundle of electromagnetic waves, light itself, and confine it in a region small enough and intense enough that the energy of the light curved space-time enough to hold the light in place. Light has no rest mass. A photon's rest mass is exactly 0. And yet, Wheeler realized, a sufficiently concentrated packet of pure field energy would gravitate, because in Einstein's equation it is energy, not rest mass, that curves space-time. In his own words from that 1955 paper, associated with an electromagnetic disturbance is a mass, the gravitational attraction of which, under appropriate circumstances, is capable of holding the disturbance together for a time long in comparison with the characteristic periods of the system. Wheeler coined 2 mottos for this that capture the whole thesis of our exploration in 4 words: mass without mass, and its cousin, charge without charge. Mass without mass. An object that weighs something, that pulls on the world, that is built out of nothing but trapped energy. If Einstein's equation is right that T mu nu is the source, then a geon must gravitate, and it does in the mathematics. Picture it, a glowing torus of light, a ring of electromagnetic energy so intense that the space-time around it curves into a well deep enough to trap the very light that creates it. From a distance, you could not tell it from a small star or a dark, massive body. It would bend the paths of things passing near it. It would have a mass you could weigh by watching how it pulled. And there would be no matter inside it at all, only Wheeler's mass without mass. We will return to geons because their fate, whether such an object can actually be stable, turns out to matter for a modern question about the dark universe. For now, keep this image in mind. It is the purest possible illustration of our thesis. Gravity does not require matter. It requires energy momentum. And light alone, confined, would do. The competing considerations start to gather here, and I want to lay them out fairly before we go deeper. On one side sits the plain reading of general relativity, verified for a century. The source of gravity is the stress-energy tensor, full stop. On another side sit deep and unresolved questions that this same framework opens up. Questions about whether gravity is even fundamental, about what dark energy is, about what happens to the very idea of mass at the smallest scales. We are going to hold the confident, tested science and the open frontier side by side, and be honest about which is which. But first, we need to see the tested science do something dramatic. And for that, we go to the place in the universe where pressure and gravity fight to the death. A neutron star is what remains when a massive star exhausts its fuel and its core collapses. Gravity crushes the core so violently that electrons and protons are forced together into neutrons, and the whole object, as heavy as our Sun or more, is squeezed into a sphere only about 12 kilometers across, roughly 7.5 miles, the size of a small city. The density is almost incomprehensible. Around 10 to the 15th grams per cubic centimetre, about 10 times the density of an atomic nucleus, some 14 orders of magnitude denser than the densest ordinary metals like osmium or iridium, which top out around 22.5 grams per cubic centimetre. A sugar cube-sized piece of neutron star would weigh about as much as all of humanity combined. What holds such an object up against its own gravity? Pressure. Specifically, neutron degeneracy pressure, a quantum mechanical resistance that arises because neutrons, like all particles of their type, refuse to occupy the same quantum state. Cram them close enough, and they push back with tremendous force. This pressure keeps a neutron star from collapsing further into a black hole. But here, Einstein's insight that pressure gravitates becomes a matter of survival. The equation that governs the internal structure of such a star is the Tolman-Oppenheimer-Volkoff equation, derived in 1939 by Richard Tolman and, independently, by J. Robert Oppenheimer and George Volkoff. It is the relativistic version of the simple balance that keeps any star in equilibrium. At every depth, the outward push of pressure must balance the inward pull of gravity. The equation reads dP dr equals minus g times rho plus p over c squared times m plus 4 pi r cubed p over c squared, all divided by r times the quantity r minus 2 g m over c squared. Do not be intimidated by its length. Look instead at where the pressure P appears. In Newtonian gravity, the balance equation would have the density ρ pulling inward and pressure only pushing outward. But look at the relativistic terms. In the first factor, we have not ρ alone, but ρ plus P over c squared, pressure added to the density as a source of gravity. In the second factor, we have not the mass m alone, but m plus 4 pi r cubed p over c squared, again pressure adding to the gravitating content. Pressure appears on the source side of the equation. The very thing pushing outward to hold the star up is also, in Einstein's gravity, pulling inward. This is the strangest consequence in all of stellar physics, and I want you to feel its full weight. In an ordinary object, if gravity threatens to crush you, you push back harder, you increase the pressure, and you win. But in a sufficiently relativistic star, when you push back harder, you increase the pressure, and pressure gravitates. So you also increase the gravity trying to crush you. Beyond a certain point, the TOV limit, this becomes a losing game. Adding pressure to resist collapse feeds the collapse. There is no configuration of matter, no equation of state, however stiff, that can hold the star up. It must become a black hole. The original Oppenheimer-Volkoff calculation, using a simple model of non-interacting neutrons, gave a limit of only about 7/10 of a solar mass. Modern calculations, accounting for the complicated ways neutrons interact at these densities, put the TOV limit somewhere between 2 and 3 solar masses, depending on the time. True equation of state, which is still not fully known. And here, observation meets theory in the most satisfying way. In 2021, using NASA's NICA X-ray telescope aboard the International Space Station, astronomers measured the most massive, precisely known neutron star, a pulsar named PSRJ 0740 plus 6620, at about 2.08 solar masses, roughly 4 times 10 to the 30th kilograms, packed into a radius of around 12 to 14 kilometers. It sits near the edge of what the TOV equation allows. It exists right at the frontier, where pressure is losing its battle. Think about a structural engineer designing a column to hold up a roof. In every ordinary situation, if the load grows, she adds strength to the column, and it holds. But imagine a bizarre material where adding strength to the column also added weight to the roof, where the very act of reinforcing the support increased the load it had to bear. There would be a hard ceiling beyond which no reinforcement could help, because strengthening and loading had become the same act. That is a neutron star at the TOV limit. That is pressure gravitating. What does it mean that the force holding a star up is also part of the force tearing it down? It means that in Einstein's universe, there is no such thing as a purely supportive pressure. Every push carries a gravitational cost. And it is a direct observable consequence of the claim we started with. Gravity's source is the stress-energy tensor, and pressure is one of its diagonal entries. When we see a neutron star teetering near 2 solar masses and no heavier, we are watching that tensor entry do its work. Newton's mass-only gravity cannot explain the TOV limit at all. It requires pressure to gravitate, and pressure does. Now let us turn to a different entry in the tensor, the off-diagonal components, the ones that encode momentum and flux. If Einstein is right that momentum curbs spacetime, then a spinning body should do something a still body does not. It should drag spacetime around with it, twisting the very geometry in the direction of its rotation. This effect is called frame dragging, or the Lenz-Thirring effect, after Joseph Lenz and Hans Thirring, who predicted it in 1918, just 3 years after Einstein's equations appeared. Picture a bowling ball resting on a stretched rubber sheet, the classic image of mass curving space. Now imagine the bowling ball is spinning, and the sheet is not just rubber, but thick honey. The spinning ball drags the honey around with it, creating a swirl. Anything floating in that honey near the ball gets carried along, not because the ball touched it, but because the medium itself is being twisted. Frame dragging is spacetime being twisted by rotation. And crucially, it is caused not by the scalar mass of the spinning body, but by its angular momentum, a flow of momentum encoded in those off-diagonal T0I components of the stress-energy tensor. A body's mass does not know it is spinning. Its angular momentum does. And the angular momentum produces the twist. How do you measure the twisting of space-time around a planet as ordinary as Earth? The effect is fantastically small, and the experiment to detect it ranks among the most extraordinary in the history of physics. It was called Gravity Probe B, a joint NASA and Stanford mission led by the physicist Francis Everett, launched on the 20th of April 2004 into a polar orbit 642 kilometers up, about 400 miles. Its instruments were 4 gyroscopes, spinning spheres of fused quartz coated in niobium, so perfectly round that if one were scaled up to the size of the Earth, its highest mountain would be about 8 feet tall. They rank among the most perfect spheres ever manufactured by human beings. These gyroscopes were chilled in superfluid helium to below 2 Kelvin, around minus 271 degrees Celsius, minus 456 Fahrenheit, and set spinning. A perfect gyroscope in space, according to Newton, should keep its spin axis pointed at a fixed distant star forever, undisturbed. Gravity Probe B pointed its gyroscopes at a guide star, IM Pegasi, and watched for a full year whether their axes drifted. If Einstein was right, 2 things should happen. First, the geodetic effect. As the gyroscope orbits through the spacetime curved by Earth's mass, its axis should slowly tip, a predicted drift of about 6,606 milliarcseconds per year. Second, and far smaller, the frame dragging effect. Earth's rotation should drag spacetime around and twist the gyroscope's axis sideways, a predicted drift of about 39 milliarcseconds per year. To grasp how small that frame dragging angle is, 37 milliarcseconds per year is roughly the angle you would accumulate to sweep out a single degree over about 100,000 years. It is the width of a human hair seen from 10 miles away. And they measured it. The final results, published in 2011 in Physical Review Letters, gave a geodetic drift of minus 6,601.8 milliarcseconds per year, against a prediction of minus 6,606, an agreement to better than 1/3%. And the frame dragging drift came in at minus 37.2 milliarcseconds per year, against the prediction of minus 39.2. Everett, reflecting on the achievement, noted that after 31 years of research and development, 10 years of flight preparation, a year and a half in orbit, and 5 years of data analysis, the team had arrived at the final results for this landmark test of Einstein's theory. Sit with what was actually measured. Earth's rotation, its angular momentum, a flow of momentum with no bearing on its scalar mass, twists the spacetime around it, and a gyroscope 400 miles up feels that twist. This is momentum-sourcing gravity, directly observed. A non-rotating Earth of exactly the same mass would produce the geodetic effect, but not the frame dragging. The difference between them is pure angular momentum. The off-diagonal entries of the stress-energy tensor are not a mathematical decoration. They reach out and turn a gyroscope. We will return to Gravity Probe B in the synthesis, because its 2 numbers, the large geodetic effect and the tiny frame dragging effect, together map 2 different faces of the same tensor. Keep both numbers in mind. There is one more entry in this ledger I want to show you before we go deeper. And it is perhaps the strangest of all, because it happens in pure vacuum, with no matter present whatsoever. When two black holes spiral together and merge, they send out ripples in spacetime, gravitational waves, that stretch and squeeze space as they pass. On the 14th of September 2015, the two LIGO detectors in Hanford, Washington and Livingston, Louisiana, caught the first such wave ever directly detected, from the merger of two black holes about 1,300 million light-years away. The event, called GW1 50914, involved black holes of about 36 and 29 solar masses merging into one of about 62 solar masses. The arithmetic does not balance. 36 plus 29 is 65, not 62. About 3 solar masses worth of mass energy vanished, radiated away as gravitational waves in a fraction of a second, at a peak power of around 3 times 10 to the 49th watts, briefly outshining, in raw power, all the stars in the visible universe combined. Now, here is the prediction that reveals gravity feeding on itself. General relativity says that after a gravitational wave passes through a region, the freely floating test masses there do not return exactly to their original separations. Space is permanently, if minutely, rearranged. This is the gravitational wave memory effect. There are two versions: the linear memory, predicted by Yakov Zeldovich and Bohdan Polnarev in 1974, and the nonlinear memory, worked out by Dimitrios Christodoulou in 1991. And the nonlinear memory matters most for our thesis because of what sources it. It is sourced by the energy carried by the gravitational waves themselves. The waves carry energy momentum. Energy momentum sits in the stress-energy tensor, and so the waves gravitate. They leave a permanent curvature behind, a scar on the vacuum, produced by nothing but the energy of gravity itself. Gravity begets gravity, in empty space with no matter anywhere in sight. Picture 4 beads floating in a perfect square in the void. A gravitational wave sweeps through. The beads jitter and stretch as it passes, and when it is gone, they settle into a slightly different arrangement than before. The square is subtly deformed, forever. The vacuum remembers. What does it mean that empty space keeps a permanent record of a wave that took a fraction of a second to pass? It means that the source of gravitation is genuinely energy momentum, not matter, because here there is no matter at all, only the energy of the field, and it curves space and leaves that curvature behind. As of now, this memory effect has not been individually detected. A 2024 analysis of the GWTC3 catalogue of gravitational wave events concluded that definitive evidence of memory will likely require an ensemble of around 2,000 detected events against the roughly 90 searched so far. So, this particular prediction remains confirmed in theory, but awaiting direct observation. That is exactly the kind of distinction we will keep sharp: what the evidence has shown and what it has not yet shown. So, let us take stock of what we have laid out, because we are about to go deeper still. We have seen that Einstein's field equations name the stress-energy tensor, not mass, as the source of gravity. We have seen four faces of that tensor at work: energy density everywhere, pressure gravitating inside neutron stars and setting the TOV limit, momentum and angular momentum twisting space-time, measured by gravity probe B, and pure field energy, leaving permanent memory in the vacuum. And we have seen that even the mass we do have is, in the proton, about 99% energy. Every strand points the same way. Now we deepen it, and we bring in the more radical possibility that has grown at the frontier, that gravity itself, and even space-time, might not be fundamental at all, but emergent, from energy, from thermodynamics, from information. To understand why serious physicists began to suspect this, we have to go back to an unlikely place: the thermodynamics of black holes. In the early 1970s, Jacob Bekenstein, then a graduate student, proposed something that sounded absurd. He suggested that a black hole has entropy, a measure of disorder or hidden information, and that this entropy is proportional not to its volume, as you might expect, but to the area of its event horizon, the surface of no return. His reasoning was subtle. If you drop something with entropy into a black hole, the entropy seems to vanish, threatening the second law of thermodynamics, unless the black hole itself gains entropy to compensate. Stephen Hawking initially resisted the idea. Then, in 1974 and 1975, proved something even more startling. Black holes are not perfectly black. They radiate. Through quantum effects near the horizon, they emit a faint thermal glow, Hawking radiation, and therefore have a temperature. And once you know a black hole has a temperature, thermodynamics forces it to have a definite entropy, and Hawking fixed the exact value. The result is the Bekenstein-Hawking entropy formula, one of the most profound equations in physics. S equals k c cubed a over 4 h bar g. In plain terms, the entropy S of a black hole equals its horizon area, A, multiplied by a combination of fundamental constants: Boltzmann's constant, K, the speed of light, c, Planck's constant, h bar, and Newton's gravitational constant, g, and divided by 4. More compactly, the entropy equals the horizon area, measured in units of the Planck area, divided by 4. Look at what constants appear in that single formula. The speed of light from relativity, Planck's constant from quantum mechanics, Boltzmann's constant from thermodynamics, Newton's constant from gravity. All four great pillars of physics meet in one equation about the area of a black hole. No one has fully explained why, and it was the first hint that gravity, quantum mechanics, and thermodynamics are secretly the same story. Here is the part that reorganizes the picture. Entropy scales with area, not volume. This is deeply strange. If you want to know how much information can be stored in a region of space, you might think it scales with the volume. More room, more storage. But black hole thermodynamics says the maximum information in any region is set by the area of its boundary. This is the seed of the holographic principle. The idea that the full description of a volume of space can be encoded on its surface, like a three-dimensional scene captured on a two-dimensional hologram. And if that holds, then the space inside, the geometry, the very fabric that curves, might be something that emerges from information living on a boundary rather than being fundamental. I want to be careful and honest here, because we are now moving from tested science into theoretical frontier. Everything about neutron stars and gravity probe B and the Proton is established, measured, confirmed. What follows, emergent gravity, holography, the idea that space-time is woven from entanglement, is serious, mathematically rich, and pursued by some of the finest minds in physics. But it is not confirmed. It is where the field is reaching. I will flag the line clearly as we cross it. The first person to take the thermodynamic hint and run with it all the way to Einstein's equations was Ted Jacobson in a 1995 paper with a title that says everything: Thermodynamics of Spacetime, the Einstein equation of state. Jacobson asked a radical question. What if Einstein's field equations are not a fundamental law at all, but a thermodynamic relation, like the equation that relates the pressure, volume, and temperature of a gas? The ideal gas law is not a deep truth about the fundamental constituents of air. It is a statistical statement that emerges when you have enormous numbers of molecules. What if gravity works like that? Jacobson took the fundamental relation of thermodynamics, the Clausius relation, delta Q equals TdS, which says that heat flow, delta Q, equals temperature T times change in entropy, ds, and applied it not to a gas, but to space-time itself, specifically to what an accelerating observer sees. An accelerating observer, by a result called the Unruh effect, perceives empty space as warm. They see a temperature where an inertial observer sees none. Jacobson demanded that the Clausius relation hold for every such local horizon at every point in spacetime, with the heat being the flow of energy across the horizon and the temperature being the Unruh temperature. And out of that demand, using nothing but thermodynamics, the Einstein field equations emerged. In his words, viewed in this way, the Einstein equation is an equation of state. Think about what that would mean. When you derive the ideal gas law from thermodynamics, you do not then try to quantize the gas law to find the atom. The gas law is not fundamental. The atoms are, and the gas law emerges from their statistics. Jacobson's suggestion at the end of his paper was equally provocative. It may be no more appropriate to quantize the Einstein equation than to quantize the equation for sound waves in air. Sound is real, but it is not fundamental. It is a collective behavior of air molecules. Perhaps gravity is real, but not fundamental. A collective thermodynamic behavior of something deeper. And notice how naturally this fits our thesis. If the Einstein equation is an equation of state relating energy flow to entropy and geometry, then energy, once again, not mass, is the protagonist. Consider a diver looking up at the shimmering underside of a pool's surface. The surface tension, the ripples, the way the surface pulls itself flat, these are real, measurable forces. But there is no surface force among the fundamental laws of physics. Surface tension emerges from the collective attraction of countless water molecules. Jacobson's proposal is that Einstein's gravity is a surface tension of spacetime, real, precise, but emergent from the statistics of unseen microscopic degrees of freedom. This is a genuinely open question, not a settled result. But it is a serious and beautiful one. In 2010, the physicist Erik Verlinde pushed this line of thinking in a striking direction, with a paper titled On the Origin of Gravity and the Laws of Newton. Verlinde argued that gravity is not merely thermodynamic, but specifically an entropic force, the same kind of force that makes a stretched polymer molecule want to contract. When you stretch a rubber band, it pulls back. That restoring force is not due to any fundamental attraction between the atoms along its length. It is entropic, arising because the coiled-up, disordered state has vastly more configurations than the stretched-out, ordered one. The rubber band pulls back because disorder is statistically favored. Verlinde proposed that when a mass approaches a holographic screen, an imagined surface encoding information about the region, the change in the information's entropy produces a force. And that force, worked out, is exactly Newton's gravity. His governing relation is compact. F delta x equals T delta S. Force times displacement equals temperature times change in entropy. Verlinde opened his paper with a line worth quoting, because it names our theme precisely. Of all forces of nature, gravity is clearly the most universal. Gravity influences and is influenced by everything that carries an energy and is intimately connected with the structure of spacetime. Everything that carries an energy. Not everything that has mass, everything that carries energy. Verlinde later extended the idea in 2016 into a covariant emergent gravity theory that attempts to account for the extra gravity we normally attribute to dark matter by adding a contribution from the entanglement entropy associated with dark energy. For a single point mass, his theory reduces to a modified law of gravity known as MOND. And here, the frontier gets tested against hard data, which is exactly where we should be careful. MOND, Modified Newtonian Dynamics, was proposed by Mordechai Milgrom in the early 1980s as an alternative to dark matter. The problem it addresses is real and stubborn. Galaxies rotate too fast. If you add up all the visible matter in a spiral galaxy, the stars, the gas, and apply gravity, the outer parts should orbit slowly, the way distant planets orbit the Sun more slowly than close ones. Instead, they orbit at nearly constant speed all the way out, as if there were far more gravitating stuff than we can see. The mainstream explanation is dark matter, vast halos of invisible matter whose gravity holds the galaxies together. MOND's explanation is different. Perhaps gravity itself changes at very low accelerations, becoming stronger than Newton predicts, with no need for invisible matter. MOND is remarkably successful at the scale of individual galaxies. It predicts a tight relationship between how fast a galaxy rotates and how much visible matter it contains, the baryonic Tully-Fisher relation, and a tight radial acceleration relation between the gravity we observe and the gravity the visible matter alone would produce. These relations are observed, and they are hard for the dark matter picture to explain so cleanly. But MOND fails badly at larger scales. In clusters of galaxies, it does not provide enough extra gravity, and it struggles to explain the cosmic microwave background and the large-scale structure of the universe, which dark matter accounts for beautifully. Valinda's emergent gravity was exposed to a sharp test in 2017, when Federico Lelli, Stacey McGaw, and James Schombert compared it against the SPARC database, a collection of 175 disk galaxies with carefully measured rotation curves. They found that Valinda's theory, to fit the data, required implausibly low ratios of stellar mass to starlight, and predicted correlations in the scatter of the radial acceleration relation, a dependence on galaxy size, that are simply not seen in the data. Other analyses, under different assumptions, reported more reasonable fits. And foundational critiques by Sabine Hossenfelder and others argued that Valinda's derivation, while suggestive for the Newtonian case, is essentially a reinterpretation with real gaps when extended to full general relativity. So, the honest status of emergent gravity is this: conceptually provocative, tied to the deep thermodynamic clues, but in tension with detailed galactic data, and lacking a complete relativistic formulation. It is not a replacement for general relativity. It is a hint that something deeper may be going on. There is a related hybrid worth naming, because it shows physicists trying to have the best of both pictures. In 2015, Lasha Beregiani and Justin Khoury proposed that dark matter might be a superfluid, a bizarre quantum state of matter, like ultra-cold helium, that flows without friction. In their theory, dark matter is made of extremely light axion-like particles that, in the cold, dense cores of galaxies, condense into a superfluid. The phonons, the sound-like ripples in that superfluid, mediate an extra force on ordinary matter that mimics MOND, explaining galactic rotation curves. But in galaxy clusters, where the particles move too fast to condense, the dark matter behaves normally, preserving the successes of standard cosmology. It is an elegant attempt to unify the galaxy-scale success of MOND with the large-scale success of dark matter. Its weaknesses are real too. It appears to underpredict the stellar masses inferred from gravitational microlensing, and it is heavily model-dependent. Under test, not confirmed. Notice the pattern across all of this. Whether it is Jacobson's thermodynamic derivation, Valinda's entropic force, or the ongoing dark matter debate, the quantity doing the work is consistently energy, entropy, and information, never bare mass. Even the theories that compete with each other agree on that. Keep this in mind. We will weigh these competitors directly in the synthesis. Now I want to take you to what may be the most radical idea on this frontier, the proposal that space-time geometry itself is built out of quantum entanglement. This is where gravity's source is energy transforms into something even stranger. Gravity's very stage, space-time, may be woven from quantum information. The story runs through holography. In 1997, a framework emerged, a precise mathematical correspondence between a theory of gravity in a certain curved space-time and a theory without gravity living on its boundary. It is a concrete realization of the holographic principle, a three-dimensional gravitating world fully described by a two-dimensional theory on its edge. And in 2006, Shinsei Ryu and Tadashi Takayanagi discovered something beautiful within this framework. They found a formula connecting entanglement, the quantum correlations between parts of the boundary theory, to geometry in the interior. The Ryu Takayanagi formula reads S sub A equals the area of gamma A divided by 4gh bar. In words, the entanglement entropy of a region A on the boundary equals the area of a certain minimal surface reaching into the bulk divided by 4 times Newton's constant times Planck's constant. Look at the structure of that equation and compare it to Bekenstein-Hawking. Both say entropy equals area over 4g. But now the area is not a black hole horizon, it is a surface deep in the geometry. And the entropy is not thermal disorder, but quantum entanglement. Ryu Takayanagi says that entanglement in the boundary theory is geometrically encoded as area in the bulk. Where there is more entanglement, there is more connected geometry. The physicist Mark van Ramsdonk drew the startling conclusion in 2010. If entanglement builds geometry, then removing entanglement should tear geometry apart. Take two regions of the boundary that are highly entangled, and the bulk between them is a smooth, connected space-time. Gradually reduce the entanglement, and the geometry pinches, stretches, and finally splits into two disconnected pieces. Entanglement is the thread stitching space-time together. Cut the threads, and space-time falls apart into disconnected fragments. Consider a chain-mail garment. From a distance, it looks like a continuous, flexible sheet of fabric. But it is made of thousands of individual rings, and it holds together as a sheet only because those rings are linked. Cut enough links, and the fabric is no longer a fabric at all, just a pile of separate rings. In this picture, space-time is the fabric, and quantum entanglement is the linking of the rings. The smooth continuum we experience is what emerges when the microscopic degrees of freedom are richly entangled. This idea reached its most vivid form in 2013, when Juan Maldacena and Leonard Susskind proposed what they called ER equals EPR. The name combines two famous 1935 papers, both involving Einstein. ER stands for Einstein-Rosen, who described bridges through space-time, what we now call wormholes. EPR stands for Einstein, Podolsky, and Rosen, who described quantum entanglement, the spooky action at a distance between correlated particles. Maldacena and Susskind proposed that these two apparently unrelated 1935 ideas are secretly the same thing. Two entangled particles are connected by a tiny, non-traversable wormhole. Entanglement is a wormhole. Geometry and quantum information are two descriptions of one reality. I have to be scrupulously honest about the status of this. ER equals EPR is a conjecture. It is not proven, and at face value, it involves conceptual tensions between the mathematics of quantum theory and the mathematics of classical gravity that specialists are still working through. It is best understood as a deep heuristic, anchored by the provable Ryu-Takayanagi formula in specific settings. It is not established physics. But it is a serious proposal by serious physicists, and it points in the same direction as everything else, away from mass as fundamental, toward energy, entropy, and information as the architects of geometry itself. There is one more frontier program I want to lay beside these, because it attacks the same question. What is space-time made of from a completely different direction? It is loop quantum gravity. Where the holographic ideas grow out of string theory and information, loop quantum gravity grows out of taking general relativity itself and applying the rules of quantum mechanics directly to the geometry of space. It began with Abhay Ashtekar's 1986 reformulation of Einstein's theory into variables better suited to quantization. And it advanced dramatically in 1995 when Carlo Rovelli and Lee Smolin proved a remarkable result. In this framework, the geometric quantities we take for granted, area and volume, are quantized. They cannot take just any value. Area, in particular, comes in discrete chunks, with the smallest non-zero possible value, an area gap, of roughly the Planck area, about 2.6 times 10 to the minus 70 square meters. Let that sink in. In loop quantum gravity, you cannot have a patch of area smaller than about 10 to the minus 70 square meters. Space is not a smooth continuum that you can subdivide forever. It is granular at the Planck scale, the scale set by the Planck length, about 1.6 times 10 to the minus 35 meters, where quantum mechanics and gravity must merge. The fundamental states of geometry are described by objects called spin networks, introduced originally by Roger Penrose, in which edges carry units of area and nodes carry units of volume. Space, in this picture, is a woven network of discrete quantum threads, and the smooth space-time of our experience is the large-scale appearance of that weave. Picture a photograph of a beach that looks, from across the room, like a smooth expanse of tan. Walk up to it, and you see it is printed from discrete dots of ink. Pick up a handful of the actual sand, and you find discrete grains. Loop quantum gravity says space-time works like that. Smooth from far away, granular up close, with the grains being quanta of geometry. And notice what happens to mass in such a picture. If space itself is discrete quanta of area and volume, then the notion of a localized rest mass sitting at a point becomes problematic, because there are no points, only the finite quantum cells of the spin network. The very idea of mass at a location dissolves into the combinatorics of the network. I want to be as honest about loop quantum gravity's limits as about the holographic programs. The discreteness of area and volume is derived on what physicists call the kinematic level, the description of the possible states of geometry. But the dynamics, how those states evolve, governed by what is called the Hamiltonian constraint, remains unresolved, plagued by ambiguities in how the mathematics should be ordered. Loop quantum gravity has not been experimentally confirmed, and the Planck scale, where its effects would appear, is some 10 to the 19th billion electron volts in energy, hopelessly far beyond any conceivable direct experiment. So this too is a frontier, not a settled result. But it is a frontier where, once again, mass is not fundamental. We now have, laid out fairly, the full landscape. On the confirmed side, general relativity, verified to extraordinary precision, in which the stress-energy tensor, energy, momentum, pressure, stress, is unambiguously the source of gravity, and rest mass is one small entry. On the frontier side, a family of proposals, Jacobson's thermodynamics, Verlinder's entropic gravity, Ryu Takayanagi and ER equals EPR, loop quantum gravity, all suggesting that gravity, and perhaps space-time itself, is emergent from something deeper, and all agreeing that the something deeper is energy, entropy, and information, not mass. And threaded through all of it is one more open question, the biggest of all, which touches the cosmological constant lambda that we set aside at the very beginning. It is time to return to it, and then to weigh everything. Earlier, I said we would come back to lambda, the cosmological constant sitting in Einstein's equation. Now we do. Lambda represents the energy of empty space itself, the vacuum energy. Even with no matter present, the vacuum has a stress energy of its own, and it gravitates. In the standard model of cosmology, called lambda CDM, this vacuum energy is a constant, driving the accelerating expansion of the universe that was discovered in 1998 through observations of distant supernovae. It is what we call dark energy. And in lambda CDM, its equation of state, the ratio of its pressure to its energy density, written W, is exactly -1, the value for a true cosmological constant that never changes. But here, a fresh crack has appeared, and it goes to the very heart of our thesis, because the question is whether the vacuum's own stress energy is constant or dynamical. The Dark Energy Spectroscopic Instrument, DESI, operating at Kitt Peak in Arizona, has been mapping the positions of millions of galaxies to measure how the expansion of the universe has changed over time. Its first data release in April 2024 and its second in March 2025, combined with observations of the cosmic microwave background and distant supernovae, hinted at something the standard model does not predict. Dark energy may not be a constant after all. It may be evolving. Physicists parameterize this possibility with an equation of state that changes over cosmic time. W of A equals W0 plus WA times the quantity 1 minus A, where A is the scale factor describing the size of the universe. W0 is the present value, and WA describes how it evolves. For a true cosmological constant, W0 would be -1, and WA would be 0. DESI's data, depending on which supernova sample is included, prefer a W0 somewhat greater than -1 and a WA that is negative, an evolving dark energy over the constant, at a statistical significance ranging in the 2025 analysis from about 2.8 to 4.2 standard deviations. That is intriguing, even tantalizing, but it is not yet decisive. The threshold physicists conventionally demand for a discovery is 5 standard deviations. And there are real worries that the preference is partly driven by subtle systematic errors in the low redshift supernova measurements, or by smoothing effects in the cosmic microwave background data. It is an open question, honestly unresolved. But consider what it would mean if it holds. It would mean the energy of the vacuum, the T mu nu of empty space itself, is not a fixed constant of nature, but a dynamical thing, changing as the universe evolves. It would mean that even at the largest scale, the scale of the whole cosmos, gravity is being sourced by an energy content that is alive and changing, not by any static quantity. What does it mean that the emptiest thing there is, the vacuum, might carry an energy that shifts over billions of years, steering the fate of everything? We do not yet know, but the question itself is a perfect capstone to our theme. From the proton to the cosmos, the protagonist is energy, and its behavior is where the deepest mysteries live. Now we weigh. For most of this exploration, I have laid out the evidence neutrally: the equations, the neutron stars, the satellites, the frontier theories. Let me now bring the threads together and state plainly what the evidence supports and where each explanation holds or strains. Start with the central claim, the one the title of this exploration puts sharply. Gravity is real, but mass is not its cause. On the evidence, this is not speculation. It is the settled content of general relativity, and it is confirmed from 4 independent directions. First, the proton mass decomposition. Lattice QCD shows that about 99% of ordinary matter's mass is energy: gluon fields, quark motion, the trace anomaly, with the genuine Higgs rest mass contribution at only 1 to 2%. The mass that gravitates is overwhelmingly energy. Second, the TOV equation and the observed 2 solar mass neutron stars like PSRJ 0740 plus 6620, pressure appears in the gravitational source, and the existence of a mass limit set by pressure-feeding collapse is a direct, observed consequence that Newton's mass-only gravity cannot produce. Third, Gravity Probe B. The measured frame dragging of -37.2 milliarc-seconds per year is angular momentum, momentum flux, curving space-time, with no dependence on scalar mass. Fourth, the gravitational wave memory effect predicted by general relativity, in which the energy of the waves themselves leaves permanent curvature in pure vacuum, though this fourth strand awaits direct detection, and I will not overclaim it. Weigh these against the alternative that mass is the source, the Newtonian picture. Where does it hold? At everyday scales, at low speeds and modest densities, Newton's mass-based gravity is an excellent approximation. because there the energy density is dominated by rest energy, and the pressure and momentum contributions are negligible. That is why it landed spacecraft on the Moon. But where does it strain? It strains and breaks precisely where the other tensor entries become significant. Inside neutron stars, where pressure gravitates and sets a limit Newton cannot derive. Around rotating bodies, where angular momentum drags space-time. In gravitational waves, where field energy alone gravitates. And inside the proton, where the mass itself turns out to be energy. The verdict on the science is clear, and I will state it without hedging. The evidence overwhelmingly supports the stress-energy tensor as the source of gravity. Rest mass is a real, invariant, useful label, a Lorentz scalar you compute from the form momentum. But it is a label, not the cause. Now weigh the deeper competitors, the theories about what gravity fundamentally is. Here I must be more careful, because here the evidence does not yet decide. Standard general relativity treats gravity as fundamental. Space-time curvature sourced by T mu nu, full stop, verified to 1 part in 10 to the 15th by microscope's test of the equivalence principle in 2022, which found no difference in how titanium and platinum fall to a precision of about 1 part in 1,000 trillion. That is the most stringent confirmation ever made that free fall depends only on the geometry, not on what a thing is made of, not on its composition, not on its binding energy fraction. On the evidence available, general relativity stands unrefuted. Against it stand the emergent gravity proposals. Jacobson's derivation of the Einstein equation from thermodynamics is mathematically real and genuinely suggestive. It shows that the field equations can be read as an equation of state. But it does not, by itself, prove that gravity is emergent. It shows a deep formal analogy, and analogy is not demonstration. Verlinder's entropic gravity reproduces Newton's law in a suggestive way. But, as the spark galaxy data, analysed by Lely, Magor and Schombert in 2017 showed, strains against detailed galactic observations and lacks a complete relativistic formulation, as Hossenfelder and others have argued. Where it holds, it connects gravity to the thermodynamic clues that are undeniably present in black hole physics. Where it strains, it does not yet match the data as well as general relativity plus dark matter, and it is not a finished theory. The Ryu-Takayanagi formula is provable within specific holographic settings and is genuine established mathematics. But ER equals EPR, the vivid claim that entanglement is wormholes, remains a conjecture with unresolved conceptual tensions. Loop quantum gravity derives a discrete geometry rigorously at the kinematic level, but its dynamics remain unresolved, and it has no experimental confirmation. So here is the honest resolution of the deeper question. The evidence does not yet tell us whether gravity is fundamental or emergent. What the evidence does tell us consistently across the confirmed physics and across every serious frontier proposal is that whatever gravity turns out to be, its currency is energy, momentum, entropy, and information. Not one of these programs makes rest mass fundamental. They disagree about almost everything else. They agree about that. And that agreement is itself a kind of evidence, a convergence, even if it is not proof. And then there is the edge, the place where the science reaches its limit, and it is honest to say so. Why does the Einstein equation take a thermodynamic form at all? Is the vacuum energy a fixed constant or a dynamical thing, as DESI hints but has not confirmed? Does space-time truly emerge from entanglement? What replaces mass as a meaningful local quantity at the Planck scale, where area and volume come in discrete grains? And beneath all of these sits the deepest question of all: why there is a stress-energy tensor at all? Why there is energy? Why there is anything to curve space-time in the first place? Here, the equations do not answer. Here, the measurements cannot reach. This is the ultimate origin edge, and it is beyond what the science can settle. I will not close it with any verdict in either direction, because the honest thing, the thing the evidence itself demands, is to name it clearly and leave it open. This is the part that stays with me. Not the scale, not even the precision. It is that we set out 3 centuries ago, certain that we knew what made things heavy. And the closer we looked, the more the answer dissolved from stuff into energy. And then the question of what energy fundamentally is, and why it curves the world, opened onto a mystery we have not closed. We understand how gravity works to 15 decimal places. We do not yet understand what it is. Both of those things are true at once, and holding them together is, I think, the honest posture of a curious mind. Let me bring this exploration to a close. We began with a strange claim that roughly 99% of your weight is not matter but trapped energy, and that the thing which curves the space around you is not mass, but the stress-energy tensor, T mu nu, the full ledger of energy density, momentum, pressure and stress that Einstein's field equations name as the source of gravity. We traced that claim through the perfect fluid tensor, where pressure sits inside the source. We watched it govern the interior of a neutron star through the Tolman-Oppenheimer-Volkoff equation, where pressure gravitates and sets a limit beyond which no star can hold itself up. A limit we see realized in the 2 solar mass pulsar PSRJ 0740 plus 6620. We saw momentum curve spacetime in the frame dragging measured by gravity probe B, and field energy alone leave permanent scars in the vacuum through gravitational wave memory. We went inside the proton and found through lattice QCD that its mass is overwhelmingly gluon field and quark motion energy, with the Higgs rest mass contribution a mere sliver. And we followed the frontier: Jacobson's thermodynamic Einstein equation, Verlinde's entropic gravity, the Ryu-Takayanagi formula and ER equals EPR, loop quantum gravity, and DESI's hint of a dynamical vacuum, where physicists ask whether gravity and even space-time are emergent from energy, entropy, and information. Here is what the evidence has shown. Gravity is sourced by energy momentum, not by rest mass. This is confirmed by neutron star structure, by precision equivalence principle tests to 1 part in 10 to the 15th, by measured frame dragging, and by the composition of the proton itself. Rest mass is a genuine invariant label, but it is a label, not a cause. And in ordinary matter, it is a small one. That much the science resolves cleanly. And here is what remains open, honestly. Whether gravity is fundamental or emergent. Whether the vacuum's energy is constant or dynamical. Whether space-time is woven from entanglement. And what mass even means at the Planck scale. And beneath all of it, why there is any energy to curve space-time at all. Those questions are beyond what the current evidence can settle. And the honest thing is to leave them standing, unclosed, rather than to force an answer the measurements do not support. If you found value in this exploration, consider subscribing. It genuinely helps these deep dives reach more curious minds who value the mathematics behind the wonder. And if the question of the vacuum's own energy stayed with you, that hint that the emptiest space might carry an energy that changes over cosmic time and steers the fate of everything, there is a related exploration waiting on the end screen and linked in the description, following that thread more deeply into what dark energy might be. It is the kind of open question that does not let go easily. So sit for a moment with this. The weight of your own body, the pull that holds you to the earth, the curvature that bends the light of distant stars. None of it is caused by matter in the way we once believed. It is caused by energy, woven through everything, restless and confined, bending the space it lives in. Mass was always just a name we gave to trapped energy. And it is the energy that pulls. There is a piece of the machinery I have not yet shown you directly, and it is the equation that tells a falling object where to go once space-time is curved. It is called the geodesic equation, and it reads d squared x mu d tau squared plus gamma mu alpha beta times dx alpha d tau times dx beta d tau equals 0. In plain language, the term with the second derivative describes the acceleration of the object through space-time. And the gamma symbol, the Christoffel connection, encodes the curvature that the stress-energy tensor produced. The equation says the object follows the straightest possible path through curved geometry. And notice what is absent from it entirely. There is no mass term. The object's own mass does not appear. A feather and a cannonball trace the same geodesic, because the path is set by the geometry, not by what is falling through it. This is the mathematical heart of why all things fall alike, and it connects directly to the single most precise test of gravity ever performed. That test quantifies any deviation with a number called the Ertwursch parameter, which reads eta equals 2 times a minus a minus A minus B over A minus A plus A minus B, where A minus A and A minus B are the accelerations of two different materials in freefall. If two substances fall at exactly the same rate, eta is zero. Any difference, any hint that composition matters, shows up as a non-zero eta. The microscope satellite, flown by the French and European space agencies, tested this by placing test masses of titanium alloy and platinum alloy inside ultra-sensitive electrostatic accelerometers in a drag-free orbit, and watching for the faintest difference in how the two fell around the Earth. Its final result, published in September of 2022, constrained the Eötvös parameter for the titanium-platinum pair to minus 1.5 plus or minus 2.3 from statistics and 1.5 from systematics times 10 to the minus 15. In the team's own words, they found no violation of the weak equivalence principle. Free fall does not care what a thing is made of, down to 1 part in 1,000 trillion. Think about a customs inspector weighing two sealed crates of wildly different contents, one packed with dense metal, one with light composite, and finding that the Earth pulls on them with identical devotion, to a precision finer than detecting a single grain of sand added to a fully loaded cargo ship. That is what microscope established. And it is precisely what the geodesic equation predicts. Because the titanium atoms and the platinum atoms, despite having utterly different proportions of protons, neutrons, and binding energy, different fractions of their mass locked up as QCD field energy, still follow the same geodesic. Composition is invisible to gravity. Only the geometry matters, and the geometry was set by T mu nu. There is a beautiful confirmation of frame dragging beyond gravity probe B that deserves mention, because a single measurement is never enough. Earth-orbiting laser-ranging satellites, the LAGEOS spacecraft, dense spheres studded with retroreflectors, later joined by LARES, have their orbits tracked by bouncing laser pulses off them with centimeter precision. Because Earth's rotation drags the local spacetime, the entire orbital plane of such a satellite is slowly twisted, an effect predicted by Joseph Lenser and Hans Thierring back in 1918. Tracking these passive metal spheres over years reveals that twist, an independent confirmation that the angular momentum of the Earth, a T0I component of the stress-energy tensor, momentum flux, not scalar mass, reaches out and turns the geometry through which the satellites glide. And there is a deep symmetry lurking beneath the gravitational wave memory effect that closes a conceptual loop. The permanent rearrangement of test masses after a wave passes is tied to what physicists call the BMS symmetries, named for Bondi, Vandenberg, Metzner, and Sachs, and specifically to transformations called supertranslations, subtle shifts in the fabric of space-time at infinity. The memory effect is, in a precise sense, a transition between two different but equivalent vacuum states of the gravitational field, connected by one of these supertranslations. The vacuum, in general relativity, is not a single unique nothing. It is a whole family of states, and the passage of energy momentum in a gravitational wave shifts the geometry from one member of that family to another, permanently. Empty space carries a memory because empty space has structure, and that structure responds to energy flux. I keep returning to the proton because it is the most intimate example of everything we have said. The chiral symmetry breaking that generates most of the proton's mass is a phenomenon in which the near-massless quarks, interacting through the gluon field, acquire an effective heft from the energy of their confinement. The vacuum of quantum chromodynamics is not empty either. It seethes with quark-antiquark pairs, a condensate, and it is the interaction with that seething vacuum that gives the proton the overwhelming bulk of its mass. So, when you press your hand against the table and feel its solidity, and when the Earth holds you in your chair, you are feeling, at the deepest level, the energy of confined fields, interacting with the structured vacuum of space-time itself. The generalized second law of thermodynamics, Bekenstein's insight that the entropy of matter plus the entropy of black hole horizons never decreases, tells us that this same vacuum at the largest scales obeys thermodynamic law woven directly into geometry. What does it mean that from the seething vacuum inside a single proton to the structured vacuum that remembers a passing wave, to the vacuum energy that may be steering the expansion of the cosmos, the same protagonist keeps appearing. Energy, in the vacuum, gravitating. It means the picture is seamless. There is no scale at which mass suddenly becomes the true cause. From the smallest confined field to the whole accelerating universe, it is energy momentum that curves the world. Let me bring this exploration to a close. We began with a claim that sounded almost like a provocation, that gravity is real, but mass is not its cause. And we followed it through the full architecture of general relativity. The stress-energy tensor, T mu nu, as the source in Einstein's field equations. Pressure gravitating inside the neutron star, PSRJ 0740 plus 6620, through the Tolman-Oppenheimer-Volkoff equation. Momentum twisting space-time in the frame dragging measured by Gravity Probe B and the Lagios satellites. Field energy scarring the vacuum through gravitational wave memory, and the proton's mass revealed by lattice QCD to be about 99% energy. We saw the geodesic equation carry no mass term, and microscope confirm that freefall ignores composition to 1 part in 1,000 trillion. And we walked the frontier. Jacobson's thermodynamic Einstein equation, Verlinder's entropic gravity, the Ryu-Takayanagi formula, ER equals EPR, loop quantum gravity, and DESI's hint of a dynamical vacuum energy, where the question becomes whether gravity itself is emergent. Here is what the evidence shows. The source of gravity is energy momentum, energy density, momentum flux, pressure, and shear stress, not rest mass. That is the direct content of the field equations, confirmed from every independent direction we have to test it. Rest mass is a genuine, invariant Lorentz scalar label. But it is a label, not the cause. and in ordinary matter it is a small one. What stays open is deeper, whether gravity is fundamental or emergent from thermodynamics and information, whether the vacuum's energy is a fixed constant or a dynamical thing, whether space-time is woven from entanglement, and, beneath all of it, why there is any energy to curve space-time at all. Those questions reach past what the measurements can settle, and the honest thing is to let them stand, unclosed. If you found value in this exploration, consider subscribing. It quietly helps these deep dives reach more curious minds who prefer the truth, with its edges left honest, over easy answers. And if the strangest thread here held you, that the vacuum itself carries an energy, one that may be shifting over cosmic time and steering the fate of everything, there is a related exploration waiting on the end screen and in the description that follows that question further into the nature of dark energy. It is a thread that does not let go. So, sit for a moment with the weight of your own body and know that almost none of it is the stuff you imagine. It is energy, confined, restless, woven through every particle of you, bending the space it inhabits, holding you gently to a world that is itself mostly trapped light and motion. Mass was only ever a name for that energy, and it is the energy that pulls. Good night.